This is my Texas Instruments corner. We have a TI 980A mini computer and my TMS 9900 based homebrew, and this is what we're working on today. But if you want to know more about the TI 980A, this is a project that we're actually working on over on Twitch. Every Friday night at 9:30, we go live and stay live until about 1:30 in the morning, working on a project together. And the project that we've been on recently is the TI 980A. It is a massive amount of fun working together on something as a big group project. And I look forward to it every Friday night. But if you can't join, I totally get it. I record all of our live streams on that go up on Twitch, and I upload them to a second channel called Usagi Workshop. Now, for the TMS 9900, this is a homebrew that we've been building up based around the essentially mini computer CPU that came out of a TI 990, which it would have been a totally different architecture to the TI 980, even though the names are very similar. The TI 990 CPU architecture ultimately got shrunk down onto a single chip, and that chip eventually got used in the TI 99/4 home computer. And I really like that CPU, so I decided to build up a homebrew computer based around it. In the previous episodes, we got the CPU, clock, power on reset, 2 kilowords of ROM, and 6 kilowords of RAM, all cut out on PCBs and plugged into each other. And we confirmed that that was all doing exactly what it was supposed to do. So the next step was to start work on communicating with the user somehow. And we're doing that via a data terminal, notably this TI Insight Series 10. This is a standard serial data terminal at 300 baud with a 40-column display, and it's the most adorable data terminal on the planet. So in order to communicate with this, we need to hook up something called a UART. This is something that takes serial transmission and converts it into parallel so that the data bus can see it and the CPU can then do something with that. And of course does the vice versa so that we can communicate with this data terminal. And we had something built out on a breadboard, and we ultimately got to the point where I could push a key on the data terminal that would trigger an interrupt on the CPU. It would see that, interpret the data coming in, and then echo it back out to the data terminal up here, essentially creating the world's worst typewriter. It was amazing, but it was all on this breadboard abomination, and well, the design had a lot of compromises in it. So everything kind of got put on hold for 2 reasons. 1, the design needed to be revised heavily, and 2, the entire room got a complete rearrange. And I am extremely happy with how the room came out. I'm starting to get used to where everything is, which means it's time to get back into our TMS 9900 homebrew because I love this project and I really want to see it come to fruition. So we took that old breadboard and we kind of threw it away, and we started a huge redesign that ultimately coalesced into this little block of PCBs and ICs that looks the absolute business, but is guaranteed to not work at all. So what we're gonna do is we're gonna plug this thing in today and see what doesn't work, so that way in the future we can troubleshoot it and potentially recut the PCBs to actually make it work. The first thing that we need to do is actually a bit of a baud to solve the problem of fan out. Anytime the CPU is doing anything really, it needs to hit the data bus and the address bus. But everything else in the computer is also sitting on those buses. This is going to create a lot of load, and the CPU only has so much oomph. Once we start getting more I/O plugged into this thing, the CPU is going to run out of punch. So we need to put some transceivers in between the CPU and everything else. And it turns out that there's a chip perfect for this that's called the 74LS245. These are bidirectional bus transceivers, and it's specifically meant to solve this problem. The only issue with them is that I don't really have a place to put them because I didn't design or engineer that into it. I should have thought of this earlier. So the way that my current construction is that I've got individual backplanes that hold 4 cards, and then those backplanes are connected to each other with a little interconnect piece here in the middle that also has power coming into it. And so I think we can exploit this space and stuff our 74LS245s into there, which is what I've built here with these 2 little PCBs. We've got 2 74LS245s per PCB, and these are actually going to stack onto each other. One of them you can see has very long pins sticking out the back, so they can stack just like that, and then these can plug into the back of the backplane and plug the new backplane into it. Now the ROM and the RAM are still going to be sitting directly on the CPU bus, but every single peripheral I/O that we put on after here is going to be completely isolated by these LS245s, and we should not load down the CPU any more than it already is, and that should get us going. This third backplane is going to slip in right here, just in front of the power supply. It's a little tight though. I kind of wish I had about 3 inches more space, but I think I can make this work. I then need to drill 4 holes for the standoffs the backplane will mount to, and then I'll thread the standoffs directly into the wood. This works surprisingly well, actually. After bolting down the backplane, I need to connect the bus with the buffer boards, but I first need to solder power supply wires to them. It's a little fiddly and tight to get the buffer board to pop down, but once it does, I know it's making very good connection. Then I just need to route and wire in all the power delivery. And finally pop on this second buffer board, which just pushes right down onto the extended pins from the lower one. This entire I/O system is being controlled via something called MMIO, or Memory Mapped Input Output. Essentially what this means is that the individual components of our I/O system are going to be listening to very specific memory addresses. And when they see the right address, they'll do something. And this board is decoding the addresses into individual signals that control the I/O system. The heart of it are these two 74LS138s. These are 3 to 8 decoders, but we want to make sure that these are essentially disabled whenever we're not in the correct memory range. So we have this collection of NAND gates over here on the uppermost 4 bits that will essentially disable them if the memory address doesn't start with F. Then the first 3 bits of the memory address are going to go into these 2 decoders, and then the 4th bit is going to go into an alternating enable that will turn one of them on or the other one off. Now this gives us 16 control signals, but we're really only going to need to use 12 of those. And those all run through, well, some of them run through some inverters, and then they run out to this little connector here on the side, at which point we will have a little expansion piece like this right here that just kind of moves those signals on down to the subsequent boards. Now I'm going to plug this board into the frontmost slot, and it's a little tight, but we've got plenty of clearance between the buffer boards that sit in front of it, and I think that's going to work great. Now the next board we're going to plug in is this one, and you can see it's even simpler than the last one. There's only 3 chips on here, and one of them is a 555 timer, and the third one is the real party piece here. This is a 74LS148. Even though this board is very simple, it opens up the door to a much more complex topic, and that topic is interrupts. The 74LS148 is a priority encoder. It's essentially the opposite of the LS138. You have 8 individual signals coming in, and it encodes that into a 3-bit value going out. And we're using this to set the interrupt level of whichever device is requesting an interrupt from the CPU. And ultimately, we ended up with just 4 interrupts. The first is going to be a tape drive interrupt. We haven't started building the tape drive yet, but I'm thinking a cassette drive that kind of sits right here, and that's going to be your mass storage for the system. The next 2 interrupts are for the 2 serial ports. And then the 4th and final interrupt is a timer-based interrupt. This can be quite helpful for doing multitasking and other things. So that's what the 555 timer on this board is doing. It's just generating a little pulse that triggers a SR flip-flop. And so I think I've got this set up to oscillate every 60 hertz. So every 60 times a second, I just said 60 like 8 times, 60 times a second, the CPU is going to be taking a break to service the timer-based interrupt. And really that's all there is on this board, except for there's this extra little port at the top. These are for the adorable little printer that we took a look at in a previous episode. Now I'm going to plug this card into the lastmost slot for 2 reasons here. The first is that we've got our parallel port right up here, and I want it as close as possible to the back. But the second is that our tape system, which is going to be over on this side, needs to communicate to it via this header on the back right here. So I want this card as close as possible to this header. The last 2 cards that we're going to plug in are these 2 right here, and they're pretty much the same. One is MUX port 0 and the other is MUX port 1. And the heart of these are a TR1602 UART, or Universal Asynchronous Receiver Transmitter. Now we have a 555 timer set up on both of these to set the baud rate. Normally you would do this with a crystal and a bunch of dividers, but this was the most compact way I could think of to set the baud rate because I don't have a whole lot of real estate on these boards here. Then our level conversion is happening all up here in the top left, and we're just doing this with a PNP and an NPN transistor. Now the things that have changed are how we deal with interrupts coming out of this. If we look at the schematic here, we've got two signals that we're worried about. One is THRE, which stands for Transmit Holding Register Empty. This is a flag that tells us we have finished transmitting a character and we're ready for a new one. Or DR, which stands for Data Ready, which means that we have fully received a character from the data terminal and it's ready to be read. Both of these signals go through an RC filter circuit here. So you can see that we have a 1 microfarad capacitor with a 1 kilo ohm resistor and a little diode clamp going on there. And this is essentially an edge trigger. And these go into an OR gate that then go to an inverter. And I didn't have enough space for a full other IC, so the inverter is built out of a transistor, and that sets off as set reset flip-flop built out of 2 NAND gates. And this set reset flip-flop is what is going to our priority encoder to trigger an interrupt to the CPU. So if we have a long string of characters that we want to send the user, 300 baud is quite slow, and that can take a long time to send all those characters out. So if we write our software in such a way that it's constantly pulling for the THRE signal, waiting for it to become available so it can stuff the next character in, that's gonna tie up the CPU for the entire time it takes to print that string, which means that for the other user, the CPU is effectively unusable while it's printing to the screen. If this were a single user system, this wouldn't be a problem, but because we have 2 people hitting the CPU at the same time, we have to find some way to deal with this. So by having the transmit holding register empty hit an interrupt, the CPU sees that, it can go into RAM, grab the next character, shovel that into the UART, and send it on its way. And then the CPU can wrap up that interrupt request, and it can go back to doing whatever it was doing before. So we can have a massive amount of text being printed out on one user's terminal, and the other user on the second terminal won't notice a slowdown. Now, before we go plugging these in, I'm gonna need to set the baud rate using the 555 timer here and adjusting this little potentiometer here. So I'm gonna need to use the oscilloscope to do that, which means I need to clip onto pin 3 right here. And my close friend Commodore Z sent me a whole bag of these HP clippy clips, and these things are great. They're fantastic, way better than the cheap junk that I've been using up to now. So I just need to hook that onto pin 3 just like that, and then we'll get that hooked up to the oscilloscope and see what's going on. Now I've got the UART pulled because it needs negative 12 volts, and I'm just feeding 5 volts into this thing from my little bench power supply here, because all I want to do is set the 555 timer. So I've got the supply set up to 5 volts, and yeah, there we go. We can see that the 555 timer is indeed oscillating. Let's get that set correctly now. And actually, I'm surprised to see that there's a massive amount of noise on the square wave coming out of the 555 timer. I would have expected this to be much cleaner. There could still be something wrong with my PCB, but either way, let's go ahead and turn on our measurement here and see if we can see. So we're at 570 hertz. I'm gonna have to speed this way up to get it up to 4,800 hertz. So let's see if we can go ahead and get that going. There's 800, there's 1,000, there's 2,000. I'm gonna have to readjust my horizontal scale here. There's 3 kilohertz, and that's maxed out. And here's the reason why it's too slow. This little capacitor right here, I needed to put in a 47 nanofarad, and I put in a 470 nanofarad. The little markings on it are 474, and I need those markings to be 473. I'll just use a little bit of solder braid to remove the old capacitor, and then I'll pop in and solder the new capacitor in place. And now we're back and ready to go, so I'll kick the power on. Did not fix our noise problem, but we are booking along much faster. I have absolutely no idea why it's so noisy like that. But let's at least try to get this down to 4,800 hertz. We're currently up at 12 kilohertz. There's 8, 7, 6, 5, and there we go. There's 4,800 hertz, pretty much on the money. That's going to be close enough, I think, to get us going along just fine. These two are going to go in the center slots right here. I'm just putting the second one in right now. And then I'm going to have to connect up this little piece here that connects all four of these together. And I've done this once before, and it is very fiddly. It makes a really nice affirmative connection, but it is an absolute bear to get everything aligned. Actually sliced out about 3 minutes of me fiddling with that. But yeah, there we go. Nice and connected. And it looks really amazing with all 12 cards plugged into their backplanes and all the backplanes connected to each other with power run. I'm absolutely in love with the aesthetic of this thing. I cannot wait until we get a tape drive over here with the control cards for that, because I think it's really gonna make this thing look awesome. Now I would plug it in and test it, but there's two things that we gotta do first. The first is that we have to make a cable that goes from the UART card here over to the data terminal. Now I don't really know what the IO situation on the back here is gonna look like, so I'm probably just gonna cobble something together for temporary purposes until we know how we're gonna build out the backside of this thing. The other thing that we gotta do is, even if we powered it on, there's the code that's on there does not support this new hardware. So we gotta write a completely new program that does support the hardware. On my laptop here, if we do a listing in this folder ASM990, there's a file in here called new HW test for new hardware test. So if we cat that out, right up here at the start of it, we're defining where the workspaces are for each of the interrupt levels. And each workspace has 32 bytes set aside for it, which is 16 words. These are the individual registers that we're going to be working on whenever we're on a specific interrupt level. Right below that, we're gonna define all of the memory mapped IO addresses. Now I could memorize these, and I do have them memorized, but in the future I'm likely to forget exactly, which mux0 interrupt equates to which address physically. Now below that, whenever the CPU receives an interrupt, it jumps to a very specific place in ROM, and the only thing it does at that point is load in a new program counter and a new workspace pointer. And so this block here is just defining the new program counter and workspace pointer for each interrupt level. I don't define anything after the first 8 because the hardware is incapable of going beyond that. So right below that, we've got the primary loop, and the primary loop is just nothing. It doesn't do, it jumps to itself. It's an infinite loop jumping to itself. So we have the label waste and we jump to waste. Then we get to the mux0 and mux1 interrupt code, and these two are identical. So whenever an interrupt comes in, it's gonna jump to here and run this code specifically. And what it's doing is it's stuck in a tight loop here, checking to see if the UART has finished transmitting the previous character. And if it has, it takes the character that we just received in the data ready register, and it stuffs that back into the transmit holding register and sends it on its way. And then it exits the interrupt, and everything is doing just fine after that. We do the exact same thing for mux1. And then the last little bit that we need to handle is the timer, because that timer is going to be kicking an interrupt off 60 times a second. So every time that interrupt hits, it's going to jump down to this tiny little bit of code, and all it's doing is hitting an MMIO address to reset that timer interrupt. So now all we got to do is assemble it into some binary files that we can burn to the ROMs, and I'm going to use ASM990. This is the assembler that I like to use for this. So it's just /assemble.sh, and then the file name is new HW test. And then we hit enter on that, and 64 records in, 64 records out, 1024 bytes. Looks like everything went nice and easy. If we'd gotten an error, it would have told me right there. So if I do a ls here, we can see that we have new HW test low and new HW test high.bin. So I actually need to copy those over to the mini-pro folder. So I do a cp new HW test, let's do underscore low.bin, and we're going over to /home/nakazoto/mini-pro. That should do the copy over to that, so we'll CD out of that, and then we'll do a CD into mini-pro. If I do an ls over here, we should be able to see, yep, new hardware test underscore low.bin. So now all I got to do is I got to burn that to the ROM that's sitting in here right now. And there is a little command for that called minipro-p, and then the ROM is an XLS28C16A. Doing a -S, a -W, and then the file is new hardware test underscore low.bin. We hit a return on that. It gives me an error about incorrect file size, but we don't really care because it's going to pad out the rest of it. And yeah, there we go. Verification. Okay. I just need to do the same for the high byte and then pop both of those back into my ROMs here, and then we can test this thing. Now, to be clear here, I am 100% not expecting this to work. There's just way too many things that could go wrong. There could be an error in my code. I could have massive hardware faults. A lot of this stuff I didn't test on the breadboard before cutting these PCBs, which is something that you should absolutely not do. So there's a lot of untested, unproven design going on here. And this is, as long as we don't let the magic smoke out, I'll consider that a bit of a win. So let's find out. Let's flip the power switch on. I don't see any magic smoke. It does look like we came out of reset. Yeah. But of course of course it does not work. That's not surprising. I've got two laptops out. One is slightly off the edge of the camera there. I've got the scope on the table here, the data terminal, and the TMS 9900 Homebrew. And that's because last night was Friday night. Remember how at the beginning of this episode I was saying that every Friday we go live on Twitch, and lately we've been working on the TI 980. Well, last night we decided to switch gears and take a crack at troubleshooting the TMS 9900 Homebrew. And boy, howdy, did I get a lot of stuff wrong. I'll just run through it real quick. There were two bugs in the assembly program that I wrote. We squashed those. After that, we figured out that I was using the assembler wrong, and that was producing binary that was incorrect. There was a pull down on IC0, which is one of the interrupt level pins on the CPU. That needed to be a pull up. Then on the new backplane that we cut, there was a tiny little fleck of copper between the tape interrupt pin and ground. This was forcing it into a constant interrupt request for the tape drive, which doesn't exist. Then two of the 74LS245s that are dedicated to the address bus were wired for the wrong direction. So they were in a constant battle with the CPU for superiority of the address bus. And then a third 74LS245 had a floating enable pin. And after fixing all of that, it still doesn't work. We were on this thing for like 4 hours last night, and I think we made a lot of valiant and really great progress, and that VOD's gonna get uploaded to Usagi Workshop here in probably a week or so. But we didn't emerge victorious. So I'll be right back here in a upcoming episode, although not next week's episode because that's back on the LGP21. So I don't particularly know when, but we're gonna come back to this and we are definitely gonna get it fully operational. So sorry that we didn't come out looking like heroes at the end of this one, but well, it's coming together and at least it looks great. So thank you so much for hanging out with me today, and I hope to see you in the next one.